Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to be looking at chemical equilibrium and developing the equilibrium constant. So you may recall that in previous lessons, we've seen that at fixed temperature and pressure, the criteria for chemical equilibrium can be written as the sum over all the components of the stoichiometric coefficients, nu, times the partial molar Gibbs energies for the species, and that sum will be equal to 0. But we also have the definition of partial molar Gibbs energy is the Gibbs energy of that pure species plus RT times the natural log of the fugacity of component I in the mixture divided by the fugacity of that species if it were pure at the same temperature and pressure. Now this is a function of temperature, pressure, and composition. If we combine this with our criteria for chemical equilibrium, we end up with the sum of nu I times the G for the species plus RT times the sum of the natural log of this fugacity ratio, or the sum of the nu i's times GI's for the species, the pure species, is equal to negative RT times the sum of the stoichiometric coefficients times the natural log of the fugacity of the species in mixture divided by the fugacity of the species when it's pure. Now, we can rewrite this just a little bit simpler by first I'll suppress the dependence of temperature, pressure, and composition. We can come back and refer to that whenever we need to. So moving the negative RT to the left-hand side, we end up with this is our expression. And I can use laws of logarithms to take the stoichiometric coefficient and move it over to the exponent, which then, because of the laws of logarithms, basically the log of A plus log of B equals log of A times B, gives me that this is the natural log of the repeated product of the FIs for the mixture over the pures raised to the stoichiometric power all multiplied together, then take the log. So if we use that and look at different particular phases that we might be looking at, let's consider first, for instance, a gas phase. I can write it essentially using the fugacity coefficient sort of style, and fugacity of the species in a mixture over YIP could also be grouped with F over P and just have this spare little YI out here, which just doesn't look like all that convenient a form, but remember I have expressions for fugacity coefficients that we've defined earlier. If I had an ideal gas, then I get an even simpler expression, because in an ideal gas, my species in a mixture approaches just simply the YI over P value, the F of approaches P, and so I end up with all I'm left with is the YI's. Everything else goes to 1 over 1. And so the gas compositions to the stoichiometric coefficient power becomes my repeated product. Take the natural log of that. Now what about liquids? In this case, the fugacity of I in this mixture is xi times gamma I, the activity coefficient, times the fugacity of the pure species. Of course, those cancel, leaving us with the much simpler log of the products of the xi's times the activity coefficients to the nu I powers. And finally, let's look at an ideal liquid mixture. We end up with that gamma I goes to 1 for this ideal liquid mixture, and so my expression looks very much like it did for the ideal gas, except we replace the y with x because we're discussing a liquid composition. Now, finding data for the g's in this expression is really sort of the hard part. What we find is that there are no tables, just abounding. Everywhere you look up, you can find data for G. About the only place we see G data is in the tables for reactions, for the delta H of formation and delta G of formation. And again, for this, we need to go back to our concept of standard state data. So the standard state is at 25 degrees C in 1 bar, and it says that we will have an enthalpy and a Gibbs energy of 0 for an elemental form in its simplest naturally occurring state. And we can use this data to create, just as we did for heat of reaction, we can create a Gibbs energy of reaction using the stoichiometric sum over all components of nu I times these enthalpies of formation. And this will get me the information for my sum of my delta G's at 25 degrees C in 1 bar. So if I look at this at 25 degrees C in 1 bar, we end up with negative delta G of reaction that I can easily get from tables of formation data over RT is the natural log of the product of these fugacity ratios of the species within the mixture and as a pure raised to the stoichiometric coefficient power. Now we're going to define this grouping that we see here as the activity. The activity is the fugacity of the species in the mixture relative to the fugacity of the pure in the standard state. And so this means that delta G reaction at the standard state over RT is the natural log of the product of all of these activities to the stoichiometric coefficient power. Okay, and this is again at the standard state, 25 degrees C, 1 bar. And our activities, well, if I'm an ideal gas, for instance, it's going to be the gas phase composition. If it is an ideal liquid mixture, it's the liquid phase composition. If it is a general liquid, I can use activity coefficients, Xi times the activity coefficient, and so forth. So this gives us a way of kind of a little more simply writing our expressions for Gibbs energy of reaction. Now let's use this so that we can define what is called the equilibrium constant. Now the equilibrium constant is going to be a function of temperature. It is in Sandler's book designated as K sub A of T, indicating that it's a function of temperature, but it's written in terms of activity. And it is the exponential of the negative delta G of reaction over RT. And we know that that must be the exponential of the natural log, so we end up with a product, I from 1 to the number of components, activity to the nu I power. And again, just for emphasis, we know that this is specifically where delta G of reaction is the sum of the nu I's times delta G of formation for all of my species, and this is at 25 degrees C in 1 bar. So what we'd like to do next is let's look at an example and see how we can apply this. So let's look at the reaction C2H6 going to form C2H4 plus H2, and all of these in the gas phase. We're going to carry out this reaction at 25 degrees C in 1 bar, and what we want is an expression that will describe the equilibrium mixture. So first we're going to need to figure out the delta G of reaction. So delta G of reaction is the delta G for formation of hydrogen plus C2H4 minus C2H6. And if we look those values up, I found 0, 68.43, and minus, and this was a negative 31.86, giving 100.29 kilojoules per mole. I can use this to determine K. So Ka is the exponential of the sum of the delta G of reaction, basically, 100.29 kilojoules per mole, divided by R, which in units of kilojoules per mole Kelvin, and then the temperature in Kelvin, 298 K, and I end up with Ka as 2.69 times 10 to the minus 18th. Now, let's assume that these molecules at 1 bar are going to be very much an ideal gas. In that case, I can use for activity, I can simply use the mole fraction of the gas phase components. Therefore, 2.69 times 10 to the minus 18th in terms of Y, with the stoichiometric coefficient of positive 1 for the C2H4 and H2, and negative 1 for the C2H6. So this is great. This is in terms of the mole fractions of each one of these. But remember, they're all interconnected through the extent of reaction. Now, if we assume that the feed contains only C2H6, it seems unreasonable that you would feed in to a fresh reaction the product, right? So if we make that as an assumption, then the amount of C2H4 formed is X, the extent of reaction. It's the same as the amount of H2 formed, and the C2H6 at the end is going to be the number of moles we started with minus the extent of reaction X. My total number of moles will be the number I started with, plus I've made 2 x's, lost 1 x, so plus x. And so therefore, in terms of the single variable x, the extent of reaction, we get so we get this as an expression where n naught would be some known value and we have x's everywhere. We can simplify this somewhat by clearing the denominator n naught plus x. So we end up with x squared over n naught minus x times n naught plus x, or x squared over n naught squared minus x squared. So let's consider a feed of 10 moles of C2H6. So in this case, what we're saying is that 2.69 times 10 to the minus 18th is equal to x squared over 100 minus x squared. And if I multiply both sides by 100 minus x squared and simplify this, what I end up with, well, I solve this and you end up with 2 roots. You get plus or minus 1.64 times 10 to the minus 8th. So a couple of comments about that answer. First of all, you end up with two answers. And this is common because these things tend to give polynomials, and so you'll have multiple roots. We're going to choose the root that's physically possible, which means, in this case, the positive root. I can't take numbers where, say, it shows that I created extra mass. I also can't take numbers that, have the mass go to 0 or -0 rather, or below 0. So I'm only going to take the positive root of this. The other thing here, though, to note is that this Ka value was very small, right? 10 to the -18th is a very small exponent. And so my extent of reaction was very small also. You might even say that the reaction just barely even proceeded. Conversely, we're going to find that when Ka is very large, the reaction will be said to go to completion. Now, going to completion is not possible. There's always going to be some small fragment that doesn't react, but it's going to be what we observe is that most of this. Now, other reactions will give a very strong mixture of both reactants and products. And so this value of Ka gives us a lot of information just initially looking at it. But here's the problem. What I have so far only is valid at 25 degrees C and 1 bar. So in next lessons, we're going to be looking at what happens if I need to operate at a different temperature or a different pressure. Thank you very much.